Okay, let's calculate out the frequency and how much energy this photon has, and then find it on the electromagnetic spectrum to figure out what we would call it type-wise. So if I've got meters, then from meters that must be a wavelength, so then I could be able to switch that over to a frequency using the speed of light, and then I can use Planck's constant and the speed of light to convert that into energy. So I want inverse seconds to give me my frequency. So I'm going to start with 3 times 10 to the 8th meters per second. That way my seconds is in the denominator right where I want it. And then I'll put 5.5 times 10 to the negative 7th meters here, and then the meters will cancel out.
Wait a minute. What's that? What's after the 3?
Poor penmanship.
What?
Poor penmanship.
Okay. Thank you for figuring it right.
That's about as good as it gets. So 3e8 divided by 5.5e negative 7. And so looks like I'm getting 5.5 times 10 to the 14th. And what's the unit? 1 over seconds. Okay. So I want to calculate out the energy now. So I need joules as an energy unit. So I'm going to use 6.626 times 10 to the negative 34th joules times seconds. I want to get rid of that seconds, so I'm going to use 3 times 10 to the 8th meters divided by seconds, so the second unit will cancel out. And then I'm going to use my 5.5 times 10 to the negative 7th meters to get rid of the meter unit. And then the unit I have left is joules. Times 6.626 e negative 34. And I get 3.4 times 10 to the negative 19th joules. And where this lies in the spectrum, nope. Nope. Where is it? There we go. So my wavelength was 10 to the negative 7th, right?
But it's bigger than that.
But it was 5.5 times 10 to the negative 7th, right? So it's not 9, so it could be visible, right? It could slide in there.
Close, yeah.
So then we could probably zoom in a little closer and take a peek here. So here's the visible spectrum. And so if I shift the number over to make it nanometer, so instead of being 10 to the negative 7th, I make it 10 to the negative 9th, that would make my number bigger, so it would be 550. So it would be 550 nanometers. Are we okay with me doing that unit conversion or that scientific notation conversion?
In your head? I'm okay with that in your head. If you would write on the board, that'd be cool.
All right. So 5.5 times 10 to the negative 7th, right? So if I take this decimal place and I move it this direction, what happens to this number?
It's bigger. I mean, yeah. No, wait a minute. Forget it.
It will get quite a
Do
bit
I make
smaller.
it a 6 or an 8?
8.
I make it an 8.
It's big. Oh, smaller.
So how about it's further from 0?
Yeah.
So then if I do it again, and I put a 0 in there, and I make this 550 times 10 to the negative 9th, what can I do with this thing?
Convert it to nanometers.
That is nano, right? And so then I've got nanometers.
You can do that straight from the wavelength.
Yep, absolutely. That's the only place you can do that part to get a wavelength one. So if I do that straight from the wavelength one, and I go back over to my diagram here, so it's what? Green?
So it's much more in the visible spectrum than I thought it would be.
It's,
Just by looking at 5.5 times 10 to the negative 7.
yeah, if you look at 10 to the negative 7th, that looks like it's probably in the UV spot. But if we go with the 5.5, I mean, that's kind of halfway in between 10 to the negative 6th and 10 to the negative 7th, right? So then we should probably be a little more accurate and figure out exactly what the number is nanometer wise. And so here it is, it's green light. So are you guys okay with the way I did the second calculation for the energy?
If you have 1 over S already,
Yep. Why didn't I just multiply that answer that I got for the prior problem times
Yes.
Planck's constant and get my answer straight away?
yes.
Okay, so good point. And the reason I'm not going to do that is because I was given 5.5 times 10 to the negative 7th in meters, and I can use that number to do both of my calculations. So if you can answer a question by using the given information, answer the question by using the given information, even if it's a little longer. Because this is, as we've talked about, multiple choice tests give you the answer. So the answers that they give you, what do they try to do? They try to trick you.
It'll give you a more right and a less right answer.
Well, they'll give you a trick question, which in this case, whatever your answer is for this 5.5 times 10 to the negative 14th, the number is actually 5.45 times 10 to the negative 14th. So if you're using your answer to calculate the next answer, your second answer might be off a little bit. But if you use the number that you were given in the problem, it's not off by any calculation error. Does that make sense? Every time I make a calculation and then use that answer for a new calculation, there's going to be a rounding error, correct?
Yes.
So what did I just do by using the 5.5 times 10 to the negative 7th for both of them? I eliminated the ability to have a rounding error in my second answer. So you will run into questions on long, difficult multiple choice exams where the second portion of the question will give you a rounding error if you use the answer from the first portion of the question. Does that make sense? They purposefully do that to see if you will use the original data to calculate your answer, or go an easier route by using an answer you already calculated to calculate your second piece of information. Does anybody know how long that NCLEX exam is? It's up to you. If you're nailing every single question, it could be like an hour and a half. If you're having trouble, it could be like 6 hours.
Because when you get one wrong, it gives you an easier question, right?
It gives you something closer to it. You're right. So you're like at a level 5, they give you a question, you get it wrong. They give you a level 3, you get it right. They give you a level 8 just to make sure, yeah, you do know what that premise is, or that particular idea, that topic is about. Yeah. They give you all the opportunity in the world to pass it, but only if you're willing to sit there without a bathroom break for 6 hours. So this time I'm given the frequency and I want to calculate out my wavelength and my energy. So I'm going to use, I want a distance, so 3 times 10 to the 8th meters per second, and then I'm going to use 4.5 times 10, no, that's not right. I'm going to put 4.5 times 10 to the 14th here because it's 1 divided by seconds. That's my unit. I'm going to get rid of that 1 since it doesn't matter. And then my seconds unit will cancel out and I'll just have a meter unit. And so 4.5 e negative 14 times, no, 3 e 8 divided by 4.5 e 14. So I got 6.7 times 10 to the negative 7th. So that would actually also be equal to 670 nanometers. So where this is on the spectrum, I don't know, orange, red. So calculating the energy is a little easier this time. It's just 6.626 times 10 to the negative 34th joules times seconds. And then we'll take our 4.5 times 10 to the 14th. Dang it. 4.5 times 10 to the 14th, and the seconds is in the denominator, and then that'll cancel my seconds unit out. And so 6.626 e negative 34 times 4.5 e 14. So I get 2 point, looks like 3 joules.
What's that first one that you, is that a -7 or a -8?
I got a -7.
Oh, I missed it just.
Does the energy value make sense for these two questions related to each other? The orange light had less energy than the green light. The orange light's closer to the infrared side. The green light's closer to the ultraviolet side when we're talking about a rainbow. All right, so what do you want to do about diagram and explaining the line spectra? I was thinking just something like this. So we've got an electron and it's in ground state. Say it jumps up to here. This is so the electron is in ground state. Some energy is added to the electron. The electron hops up to an excited state, so an energy level that it's not supposed to be in or doesn't want to be in. It falls back down, and in this case we had it fall down 2 steps, and each time it drops it releases a wavelength of light. And those wavelengths are going to be different wavelengths of light because they fell different distances and from different spots to different spots. So in this case this thing would be giving us 2 different color wavelengths of light. And this phenomenon explains what fun thing? What form of entertainment does this explain?
Fireworks.
Yeah, this is explaining fireworks. Evidence that light is both a wave or a particle. The evidence that it's that light is a wave, that includes bending of light, mirage, or mirage, or the shifting of an object underwater. So those are both refraction. And then the other, we've got interference. And we can see that in the bands the bands of light that are generated when I have a double slitted, it's the double slit experiment. So I have that flashlight, I've got like a piece of cardboard with two slits from, say, a butter knife, put it over the flashlight, point it at the wall, and I get dark, light, dark, light, dark, light, dark, light. So the areas where there is no light, that's destructive interference, and the areas where there is light, that's constructive interference. And what is it about light that makes it look like a particle? The photoelectric effect. So being able to move an electron only with specific amounts of energy. So light does not add to have more energy. So if one wavelength of blue light can make a solar panel work, and you have 10 wavelengths of red light, and those 10 wavelengths together have much, much more energy than the blue light, even though they have more energy than that one blue wavelength, together they can't sum up to move that electron. So it can only be moved on a wavelength per wavelength basis. And so what did Einstein call the light instead of a wave? What did he say that thing was? Acted like a photon, a tiny quanta or packet of energy. If it was acting like a wave, those packets of energy could add up to be a bigger packet of energy, but they're not behaving like a wave, they're behaving like an individual particle.